Today we will learn about Bernoulli distribution and binomial distribution, the introduction. So before moving into the technicalities, as usual, we will check some facts regarding Bernoulli and binomial distribution. Now, binomial distribution is also known as Bernoulli distribution, but that doesn't mean that the PDF is the same. So there is a whole story behind it where binomial distribution and Bernoulli distribution are both connected, and that you will understand towards the end of this video. Now, it is associated with the name of a Swiss mathematician, James Bernoulli. That is why the Bernoulli distribution got its name as Bernoulli distribution. And now this distribution expresses the probability of one set of dichotomous alternatives such as success or a failure. Now let's have a look at the Bernoulli process. So a Bernoulli process is a process in which the experiment is performed repeatedly, yielding either a success or a failure in each trial. No pattern, so there is no pattern in the occurrence of the success and failures. So the first time if it is success, in the second trial it could be a success. It's not necessary that it could be a failure. So there is no pattern in the occurrence of the success and failures. And the occurrence of the success or failure in a particular trial does not affect the occurrence or the success in the previous or subsequent trials. And what does that mean? Yes, here the trials are independent. In a Bernoulli process, the trials are independent. So in a Bernoulli process, we can sum up the Bernoulli process as an experiment where the experiment is performed repeatedly under constant conditions, yielding either a success or a failure, and there is no pattern in the occurrence of success or failure, which means that the success and failure of a particular trial does not affect the success and failure of the subsequent or the previous trial, and hence the trials are independent. Now let's have a look at the definition of Bernoulli distribution. But a random variable is said to follow a Bernoulli distribution if its PDF is given by f of x is equal to 1 if the outcome is a success and is equal to 0 if the outcome is a failure. So that is the only thing that you should be concerned with when it comes to a Bernoulli distribution. Now let's develop a mathematical model for binomial distribution under certain specific assumptions. So let's have a look at the assumptions. An experiment is performed under the same condition for a fixed number of trials, say n. So that is something similar to Bernoulli distribution. In each trial, there are only two possible outcomes, namely success or a failure. Again, it is similar to what Bernoulli distribution. Now, the probability of success here is denoted by P and it remains a constant, and the probability of failure is denoted by Q, which is equal to 1 minus P. And the trials are statistically independent. So these are the assumptions under which we are going to create a model, a mathematical model for binomial distribution. Now, how useful is this model? So let me put it in this way. If we conduct an experiment n times under the stated conditions, what is the probability of obtaining exactly x success? I know you will be a bit confused now. So let me specifically put something, an example over here. More specifically, if 10 coins are tossed together, what's the probability of obtaining exactly 2 heads? Again confused, right? So let's see how these questions can be solved by using a binomial distribution. Now let's move on to the ideology behind the binomial distribution, how a binomial distribution arises. For example, you can take a coin is flipped once. I hope you all know there will be two outcomes, namely head and tail. The probability of obtaining a head P is equal to 1 by 2, and the probability of obtaining a tail is denoted by Q, which is also equal to 1 by 2. Thus, when you add up these both, that is the probability of obtaining head and a tail, you will get 1. Similarly, if two coins are flipped simultaneously, there will be how many outcomes? Yes, 4 possible outcomes. Now, here A be the first coin and B be the second coin. Okay, so what are my answers or results? TT, TH, it can be two tails, one tail and a head and a tail, and two heads. Right, now I'm going to write the probabilities of these by considering P as the probability of obtaining the head and Q as the probability of obtaining the tail. Now, can you guess what is the probability of obtaining two tails in this experiment? Yes, it is Q square. What about this last one? Yes, that is P square. And what about the middle two? Yeah, here you will get QP and here you will get PQ. By adding this, you will get 2PQ. Now let's have a look at that. The probabilities corresponding to these results are QQ, QP, PQ and PP. Now, I just wrote it like this. QQ, instead of QQ, I wrote it Q square. Now, I combine these two, I get 2PQ and P square. Now, are you familiar with these terms? Do you recognize them? Yes, it is the expansion of Q plus P the whole square. You're right. So, these are the terms of Q plus P the whole square. Now, you can add it as you can also name it as a binomial expansion of Q plus P the whole square. Now, what is a binomial expansion? I hope you all know that, but we will come to that in detail later. Now, because Q plus P the whole square is, yeah, as I said, it is Q square plus 2PQ plus P square, right? Now, similarly, when 3 coins are tossed or flipped, let's see, 3 coins, let that be A, B and C, and if they are flipped, the following are the possible outcomes, and we will write the corresponding probabilities. Okay, so these are the possible outcomes, right? There are 8 outcomes. Any of this can happen. So these are the corresponding probabilities. Now, when you have a thorough look at the terms written over here, what do you infer from that? Yes, these terms are the result of the expansion of Q plus P the whole cube, which is the binomial expansion of Q plus P the whole cube. Yeah, that's right. So what happens if we toss n coins? So when we toss n coins simultaneously, the probabilities of various possible events of obtaining heads. Okay, now I'm going to define the event over here, that is of obtaining heads, are given by the successive terms of the binomial expansion, what? Q plus P the whole raised to n. So Q plus B the whole raised to n is equal to such a big expansion. I hope you all are familiar with this binomial expansion. Now you just consider the general term over here, which is NCR Q raised to n minus R P raised to R. Now, and also you have to consider the whole expansion. Now I'm going to write this in a tabular form. Since we have defined the event over here, that is x, defined the random variable x as obtaining the number of heads. So x can take the values from 0 to n, right? So I'm going to put that in a tabular form. So here it is the number of heads and the probability that x takes the value 0, that is the probability of x, the number of heads becoming 0, is Now, how did I got this q raised to n? So for that, I took the general term of the binomial expansion q plus p the whole raised to n. Now, what is the general expansion? General term in the expansion? NCR q raised to n minus r p raised to r. When I give the value, so what should I find out? The probability of the number of heads, right? Number of heads, when x number of heads, that is in the first case it is 0, right? So just substitute the value 0 over here. So you will get NC0 q raised to n minus r q raised to n p raised to 0. Yeah, p raised to 0 is over here. So NC raised to 0 is 1, q raised to n, p raised to 0 is again 1. You will get the answer q raised to n. Again, we have, in our case, we have said that x takes a value 0, 1, 2, 3 up to n. So when I give the values 2, 3, etc. up to n, I get the corresponding probabilities also over here. Okay, so you can have a thorough look at the probabilities that are coming in the second column. So the last probability is what? P raised to n, which is the last term in the expansion of your binomial expansion q plus p the whole raised to n. Now let's have the general form or the general definition of binomial distribution. A random variable x is said to follow a binomial distribution with the parameters n and p. Now in a binomial distribution, the parameters are n and p. Now what is a parameter? Okay, we will discuss that a bit later. That's a bit technical for you now. So just remember that a random variable x is said to follow a binomial distribution with parameters n and p if f of x is equal to ncxp raised to xq raised to n minus x, where x takes the value 0, 1, 2, 3, etc. up to n. And here q is equal to 1 minus p. P lies between 0 and 1, inclusive of both 0 and 1. N is equal to the number of trials, and P is equal to the probability of success in a single trial. So this is the general form or the definition of binomial distribution. Now there are 2 points that you have to remember. Now why is this binomial distribution called a binomial distribution? Okay, why is this distribution called a binomial distribution? Why? Because f of x is the x plus 1th term of the binomial expansion p plus q or q plus p the whole raised to n, which you have looked upon in the latest slide that was just before the definition of binomial distribution. Okay, if you have any doubt, you can go back and check. Then one more thing that you have to keep in mind, that is where I said there's a whole story behind how binomial and Bernoulli distribution are related. A binomial experiment consists of n independent Bernoulli trials such that each trial has the probability of yielding a success. So with that, I conclude today's video, and in the next video we will come up with the properties of binomial distribution. Thank you.